We already talked on binary code, same as matching code, which only allows ones and zeros. Memory chips store data in the form of electric charge. Chips are made of materials known as semiconductors, same of what transistors are made of. Entire networks of transistors and other components of microscopic size make up a memory chip. They work with electric energy to represent zeros and ones. That's because an electric pulse injects a small current into the chip, and a small unit from within retains the electrons produced by this injection of current. Now remember, atoms have three main particles: neutrons, protons, and electrons. Electrons have very little atomic mass and also very little energy per unit, and are the easiest particle to manipulate. The electric current is the flow of electrons caused by a force that makes them move, which is called voltage. On the other hand, charge is when electrons are gathered in a quiet manner, without flowing. They are forced by voltage to move cells in memory chip, and once the voltage is cut, they stay in memory cell. That corresponds to a bit in memory. Imagine every adjacent cell in memory being applied the voltage for writing ones and the voltage being cut in the cells to write zeros. A pulse of energy in volts is applied for a short instant, thus setting a bit in memory to 1. If no electric pulse is applied at a given instant, then the bit is made 0. Now, to make this more illustrative, in the actual ways data is transferred within a computer, let's have a look at this diagram. As we can only use 1 and zeros corresponding to electric pulses, we have electrical signals of these shapes. Show you. When it is in its lowest part, the voltage applied is 0, but when it reaches its highest part, the voltage can be, for instance, 1.8 volts that some RAM memories used, but this may vary depending on the chip or the computer, being also 3 volts, 1.3 volts, and some other values. So, two signals show the changes in voltage. Look carefully and you will find two signals of this type of pulse, one named clock and the other one is named data. The clock is used for synchronization and the other one is the actual data, 8-bit data. We are going to use this S letter as an example. These two blocks represent two different devices in computers. So let's say one is the processor and the other one is the memory. They share two different paths. One is for clock and the other one is for data. Since computers work really fast, do billions of operations by second, if you send data in a rush, all of a sudden, recipient may not be ready or paying attention, and may also not be able to catch every bit. The clock signal basically tells the recipient to read what's in the data signal. This is a way of synchronizing this data transfer. Now, let's make a mock of this data transfer. We are sending the letter S, as I told you, and it equates 8 bits. So, just have in mind that this low voltage of clock means that there is no voltage. So, imagine like you have a bulb, the lights in your room, and they are turned off. But when it rises too high, and it's high already, it will be like the lights are on. So remember that. Off, on, off, on, and so on. We have voltage high and voltage low. Okay. So we're going to have a look at what's the status of data at a given instant that the clock is telling us. So for instance, we have these red arrows of rising edges from 0 to 1. And at this very instant is when we do a check of what the voltage in data is. So for instance, at this particular time, it's V high, which is a high voltage, so it is 1. So let's start doing the transfer to this 8-bit memory space in the storage. So it will be in the same order, from left to right. So let's start. Check what's in the data at this instant. It is in high, so it is 1. Check again in this other time, and we have high voltage, so it is 1. Now check this, it is low, so it's 0. Again, it is 0, so it is low. Again, this one is high, so it is 1. This one is, have a look here, it is low, so it is 0. Again, this is high, so it is 1. Again, it is low, yeah, we have low, so it is 0. Okay, now in real computers, data transfers might be of size 32 of 64 bits and have more control lines than just this signal of clock. They might have several of these. But what will remain the same is the fact that we have high and low voltages and that we have synchronization systems.